So this lecture, I want to, we have discussed the small ball inequality as this sort of curiosity, justified, you could come to the conclusion it's just a curiosity. We've indicated its relevance to the theory of the discrepancy function, especially through the proof of the Roth theorem. The Schmidt theorem, and so the connection there is one of similarity of proof technique. We'll pass now to other applications where the small ball inequality is much more intrinsic to the questions. Let me begin with just recalling the Kolmogorov inequality, which Dima Bilic mentioned in his talk, and which concerns the question of integrating. You want to estimate the integral of some function on a unit cube in dimension d, and you want to sort of do it sort of empirically, so to speak. So you take a collection of points inside the unit cube and just evaluate f at those points, and then divide by the n is the cardinality of the collection of points p. Right. So cardinality, following the convention of the subject, the cardinality of this set is that. And then this is less than dn and an LP prime, say, divided by n. Notice that this term can be quite small. The Roth bound said that this always has a lower bound of order log n to some power that depends upon dimension. So you have a logarithmic term on top divided by n. So this is actually somehow that part actually looks like it depends only very weakly on dimension. And then the other term is the integral of the mixed derivative of f to the p 1 over p. So this is a sort of, this is the dual index p, so this is a sort of duality statement, and illustrates the interest in finding these collections p with where the discrepancy function is small. Again, think this is logarithmic, log n to the d minus 1 over 2. So this looks like a very favorable term. The drawback here is that all the constants that depend upon dimension are hidden here, and even in the case p equals 2, we don't know the correct behavior of the constants on dimension. I think William Chen has made such a problem a $1,000 problem, and since our understanding of the subject is still dictated so much by dyadic analysis, we're a long ways from being able to understand in precise terms the role of the constants that as a function of dimension. And that's true for much of what I'll say. Okay, so a second subject with a sort of that is related to the small ball inequality concerns compactness properties of Sobolev spaces. So I'll define the unit ball of a Sobolev space So P is the integrability index, D is the dimension, to be F such that, well, F is the integral so when I write the integral over here, 0x is a box. And then, so little f is the mixed derivative of capital F. So if I take dx1 to dxd of capital F, that's little f, and then the final condition is integral f to the p dx is less than 1. So you're in dimension D. You're requiring d derivatives to have an LPth moment. So you have a Sobolev embedding in this context. So that this is this collection of functions is contained in are continuous functions. They're continuous functions, and it is compact subset. This is compact in that space. So then there's a notion of Kolmogorov entropy, in which we measure the degree of the compactness. So set n of epsilon, p, and d to be least number of epsilon balls of radius epsilon L infinity balls of L infinity balls of radius epsilon. There I go. Now I've got the adjectives in the right order. Needed to cover. Okay. So compactness says for each epsilon this is finite number, and then the relevant conjecture here, which builds upon a very rich theory, is that the log of n of epsilon, p, and d is basically 1 over epsilon log 1 over epsilon to the d minus 1 over 2. So again, if we relax L infinity to a more friendly norm, an LQ for some finite q, then there's an analogous equivalence, which is much easier to establish. And the striking thing about this is that the dimensional dependence is weak as a function of epsilon, just as in the discrepancy function. So here, upper bound is known. So this dominates those terms, and to prove upper bound, one just has to exhibit covering. That does the job. The unknown direction of the conjecture is the lower bound. And notice for the lower bound is where you have to construct functions in the class so that provably each pair is separated by P and D? Right, P is finite number. P equals 2 is enough. So the mixed derivative is square integrable.
You assume only LP integrability for the derivatives at the beginning, you end up with it was continuous complex.
Right. Well, it's a very striking result, and it was first discovered in the Russian school by Temlikov is the expert here, by a person whose name escapes me, but and it's a very striking result, I think, because of the weak dependence upon dimension. And there's a very rich and intricate school that was built up by many people, including Temlikov, around this kind of. Oh, no, this is conjecture. So upper bound is known. I don't know who to attribute it to. Lower bound for such estimates is always the hard direction because one has to construct functions in the class so that that are large in number, so that any two are separated in the L infinity metric. That's where the small ball inequality comes in. Because the small ball inequality provides the lower bound on the L infinity norm. Now, the small ball inequality, as stated, won't do it because the Haar functions are not going to be in this Sobolev class. So there's an analogous conjecture in which one replaces Haar functions by smooth functions, smooth wavelets, essentially. So I think we will. So again, there's an elaborate subject here that was built up over an extended period of time, and Timlikov is the real expert here in this room on this subject. So just with the discrepancy function where the mixed derivative enters in the Koxma-Havlaka inequality, here there's a mixed derivative at play, and the Sobel and the small ball inequality is playing a role in providing the proofs of the lower bounds. There's a third question. A class of questions actually in probability theory, of which the closest connection to the small ball inequality concerns the Brownian sheet. Well, what's the Brownian sheet? Well, the Brownian sheet is a tensor product of Brownian motions. And in particular, the Brownian sheet on time t is an integral from 0 to t of an integral of a Gaussian white noise. And the Gaussian white noise can be formed by summing over dyadic rectangles of a Haar indexed by R times a Gaussian, IID Gaussian random variables. But now I have to take into account that the Haar functions are L infinity normalized, and so I should normalize by square root of R. So mixed derivative of Brownian motion is a white noise. The integration goes, this is function of S and ds. So Brownian sheet, the question here is that the Brownian sheet is continuous process like the Brownian motion is. One can look at the L infinity norm of this on the unit cube. Generically, this should be of order 1, obviously. And so the question of interest is, how does the probability, how do these probabilities behave? And then the conjecture is that this is basically epsilon to the negative 2, again with this kind of weak dependence on dimension. So this is theorem in dimension 2, theorem due to Talleyrand. And in higher dimensions, on both this on this question and on the earlier question about Kolmogorov entropy, there's only partial information which is derived from the work with Dmitry Bilik and Armen Vagyar-Shakyan. I should take, there's a log missing and there's a minus sign missing. Thank you for the correction. I think in order to understand the some of the things that are relevant to trying to prove the small ball inequality, I really should recall a few facts about Littlewood-Paley theory. And so we should start with dimension 1, and let me just restrict, we agree that we pay attention to f functions on 0, 1. So just the local case. And now for such function, the Littlewood-Paley square function is defined to be, the square of it is, in the first place, the integral of f plus the sum over dyadic intervals f h I squared, indicator I, and I put the I squared again because of this L infinity normalization. Thank you. Now the basic fact here that we want to appeal to is this, that f in LP is less than or equal to absolute constant square root of p s of f in P, and let me just stick on P bigger than or equal to 2. The LP norm of this is comparable to the LP norm of the square function, but I simply want, for the purposes of these talk, what I say next, I simply want to concentrate on this direction of the inequalities. And we're also interested largely in P bigger than 2. There's a corresponding behavior for P less than 2. The precise constants are known here. That is, one can put a precise constant there. This is due to Gang-Wang using a Bellman proof. This constant is known for all conditionally symmetric martingale differences. If you don't know what a Haar series is conditionally symmetric. It's important that it be conditionally symmetric. If it's not, you get P. So conditional symmetric is important. Not only that, this inequality holds for Hilbert space valued functions. And the constant is also known explicitly from the work of Gang-Wang. Gang-Wang was a student of Burkholder at the time that Burkholder was utilizing this technique that came to be called Bellman function to prove inequalities. So inequality holds. For f taking values in L2 and conditional symmetric is important. There's a nice inequality that one can derive from this formulation, closely related to it in many ways, the Chang-Wilson-Wolff inequality. which says, again, and now it's important that we work on the local case. F L2 is less than the square function of f in L infinity. So L2 is the Gaussian Orlitz space. The key point is that one way to evaluate this norm is simply to calculate the LP norms. The LP norms should grow at no more than the rate of square root of p. So if the square function is L infinity, the previous inequalities give you that fact. So the next remark is also important. If you have f in 0, 1 to the d, then there's an analogous square function actually, to write it down explicitly, I might need all of one page, but you extend, in the local case, you extend the Haar functions that we've been using to a basis, you form square function, that's the square function. There's a small complication in actually writing down a formal definition because I have to show you how to complete the Haar functions to basis, and it has a sort of tensor product definition, and then the important point for us is that an LP, so this is LP of 0, 1 to the d, this is less than P d over 2 S of f in LP. So since you're in a d-fold tensor product setting, the behavior of P is like this. This uses in an essential way the fact that the Littlewood-Paley inequalities hold for Hilbert space-valued functions. And then there's a well-known inductive proof of this estimate based on that fact. Apply Littlewood-Paley in the first coordinate, and you dominate what you get over here is an L2 valued function. But then you get to apply Littlewood-Paley in the second coordinate, and you continue. Okay, so what's a corollary? It wasn't proved this way, but the Jill Pfeiffer remarked on an extension of the Chang-Wilson-Wolff inequality, which would say that if you have f and you're in L of 0, 1 to the d, 2 over d, exp. Expel of 2 over d, so think dimension 2, then it's expel, is less than or equal to the square function of f in L infinity. Okay. One of the things I want to show you is that in certain situations there's a remarkable improvement of these inequalities. How much time is left? Okay. So in dimension, so now let's pass back to the small ball inequality. And we're thinking in particular about dimension 3. This is one of these problems where dimension 2 turns out to be too easy, and one can suspect that there is an inductive proof on dimension, but the base case is 3. And in fact, our higher dimensional arguments do use an inductive argument, but 3 is the base case. So, and so as a reminder, the basic object of interest is 2 to the negative n, a sub r h r, and you can continue, and actually I think it's already very challenging just to consider this case. So I did permit the case 0 before, but now let's just, this case doesn't have application as far as I know, but it's already very challenging. So now, and the goal is to provide lower bound on this, and the lower bound is n to the 3/2. That's the conjectured bound. And so just remember, n to the first power is obvious. L infinity dominates L2. You're done. So Ln is the average case estimate. 3/2 is the conjecture. And so now I want to consider, and the lovely argument in the two-dimensional case, we had auxiliary functions that helped us build a test function. So again, we have auxiliary functions. They're a little more complicated now. And so let's take vector and the integers, and the length of the vector is just the sum of the coordinates. And of course, we're typically interested in the case where the sum of these coordinates is the log of the volume. And then little f, so these auxiliary functions would then be the sum over dyadic rectangles such that Rj is 2 to the negative Rj, AR, HR. So this vector encodes the geometry, or the side lengths, of the rectangles that you sum over. And then the rectangles that satisfy these conditions in each coordinate j partition the unit cube. So you take the unit cube, you partitioned it into these subcubes of volume 2 to the minus n, all just translates of one another. And then on each rectangle, you either take the har if this is 1, or it's reverse if this is minus 1. So in the two-dimensional case, simplifies dramatically because of this product rule. In 3 dimensions, the product rule doesn't work because you can take choices of rectangles that agree in one side length, differ in the other 2, and still have the same volume. So let's analyze that case directly. So maybe I set G2. So this is the sum of the vectors R not equal to S of R1 equals S1. Fr times Fs. if R equals S, the product is identically 1. So there's no issue there. Let me just write it down for this slide, but I think we understand that the lengths of the vectors you have two vectors of the same length. They're distinct, but agree in the first coordinate. So in dimension 3, that means the second and third coordinates must be distinct. Okay? So, how should this term behave? Well, let me just draw a chart. And now I'm going to use the technology. This is R. This is S. So these indicates the coordinates of the two different vectors R and S that we sum over. They agree in the first place. But then in the next two places, they must be distinct. And notice, and a fact that we will use is if these two are distinct, say this one is bigger, then in the next level, that one must be the larger one. The subtext of this review of Littlewood-Paley theory was that if you're dealing with these Haar functions, you count the number of free parameters. So in dimension 1, you have one free parameter, you get square root of p. In dimension d, you get d free parameters, so you get p to the d over 2. How many free parameters here? Well, I can make a choice of coordinate here. If I can make second choice of coordinate here. Having made these two choices, that's fixed by this condition. So I get third choice of coordinate, and then I'm done. Once I've chosen those three coordinates, the chart's filled out. I have three free parameters. So then the basic result, and so this is d equals 3, is that G2 in LP is less than p to the 3/2 n to the 3/2. So the Littlewood-Paley principle sort of applies. This has equivalent formulation that G2 x L 2/3 is less than n to the 3/2. As soon as you have growth rate in LP norms to p to some power, that translates immediately into an expel norm. Okay, so this is just as a sort of useful word of warning, that if you do the same thing in dimension 4, one can then write down an more or less obvious conjecture based on what I've said here. We don't know how to prove it, and I think it may not be true. So this very crude heuristic of counting parameters for these sorts of products certainly gives you an idea of what to prove, but in terms of actually establishing the sharp value of p, that's a different story. So I'll give you a proof of this where I won't get the sharp value of p. We know the sharp value of p, but it's a more involved argument. Okay, but I'll postpone that to the afternoon lecture, I think. Instead, try to convince you that you might actually want, that this actually has something interesting to say. So just remember that, well, so let me just write as H is the sum. And so now a theorem is R equals 2 to the negative n. Whoops. Oh, now I can try this technology. So I hold it down and circle. Okay. This estimate is basically trivial. Though we're in dimension 3, the fixed volume condition reduces parameters down to two-dimensional situation. So you have n squared, you have two free choices of parameters, so you get n to the 2 over 2. And then the full power of p, that's again more or less obvious because it just takes two applications of the Littlewood-Paley inequalities to obtain this. What's true is this, provided p is not too big. So actually, for small values of p, the behavior of this in LP is Gaussian. In fact, there should be a central limit theorem here. And to the best of my knowledge, that central limit theorem is not in the literature. Okay, so I think the proof of this is useful. It's corollary to the previous estimates that I was stating. And so take H, and compute the square function in x1. So H is function on R3, so sort of a simple thing to do would simply take the square function in all of R3. But don't do that, just look at the first coordinate. So the square function, and let me just write sub 1 to indicate that we're only looking at the square function in the first coordinate of H. Just remember that this is S1 of the sum of the FRs, where the length of the R's is n. Well, this is, maybe I consider the square. This is the sum A equals 1 to n of the sum of the R's such that R1 is A. So the square function computed in the first coordinate just means you take you're going to look at the Haar coefficients in the first coordinate only. The Haar coefficients in the first coordinate are determined completely by this. Well, so square it out. So when you consider the square, the square here, you can pair an FR with itself. That's nice and simple. That's 1. Otherwise, you have two vectors of the same length that are distinct but agree in the first coordinate. So the square function, so S1 of h squared is, well, I get the case where the two vectors agree. That can occur in basically n squared ways. So, by the way, square function being constant is a good thing. Plus the sum of r not equal to s of r, but they agree in the first coordinate, fr times fs. So the second term is the term that behaves like n to the 3 halves. So you have order n to the 3 halves here, n squared there. So the n squared wins for small values of p. So this behaves like p to the 3 halves, n to the 3 halves. So now you can estimate h in LP is less than square root of p, S1 of h in LP, which is less than square root of p, you get the constant term plus this term that I call G2. It's where you have the alignment in one coordinate and one coordinate only, to the p over 2 to the 1/2. So now you get square root of p n plus p to the 3/4 n to the 3/4. And so if p is at most n to the 1/3, this term is smaller than that. So there's the argument. Okay. So the next, I think we have coffee break now, and this is a good point to stop. The next lecture will give the proof. I'll give the proof of the bounds for G2, and then the last lecture show you how to use it to prove something about the small ball inequality.